Okay, welcome back everybody. So we are now on section 6.7, which is the section I'm going to call linear differential equations more concretely, in the sense that, okay, we're going to transition away from saying these are these, sledgehammer theorems that will solve the ODE for us. All we have to do is plug it into a computer, get our solution, and we're happy. And, that can be true. Like, there's a lot of applied math out there that makes that true. In fact, there's a lot of pure math out there that makes that very true as well, because we can use these sledgehammer theorems to tell us some very important things about ODEs. But in fact, a lot of ODEs, we have to manipulate equations by hand to see kind of their special properties. So we want to reduce ourselves away from just like applying these sledgehammers over and over again. If I want to solve an ODE, I want to be a little bit more particular and understand what's happening when I solve each of these. And that's what this section is, a bit of a transition section before we get to chapter 7, where we're really going to be handling ODEs by hand. But here we are at a nice transition section, and we're going to say, all right, there's ways of solving ODEs that aren't, in particular IVPs, Cauchy problems, that aren't necessarily going to be solved with our sledgehammers. So the first thing that I want to introduce is this thing called a fundamental matrix. So if we have our lovely non-autonomous ODE, which is this, Cauchy problem that was really hard for us to solve because we had that weird Magnus expansion with the calligraphic M that was just impossible to truly compute. There's a thing called a fundamental matrix, which is a capital Y, okay? So this thing is capital Y, and it's a matrix. I should make this clear. Capital Y, and I put little lines, serifs on my capital Ys, is a matrix with the property, if I take a derivative of every entry of the matrix, that's how we would interpret d dt of y of t. If I take a derivative of every entry of that matrix, it ends up being equivalent to me acting the matrix I care about, m sub t, on my matrix. Like, in some sense, I'm factoring out an m sub t of the matrix. And that's called a fundamental matrix. And it turns out that this matrix exponential that I was computing with the Magnus expansion is in fact a fundamental matrix. But now we're going to ask ourselves a question: are there easier ways of finding capital Y sub t than this e to the script m t0 from the Magnus expansion? Because if there are easier ways of finding it, even for these, these non-autonomous problems that seem a little bit tricky on the surface with the Magnus expansion, if there are easier ways to find it just naturally, if we just like attack the problem with some standard handwritten math, then we're actually going to gain a better result faster. So that's kind of the point of this section, is maybe to handle those tricky ones. And why did I introduce this idea? Why? Because we're basically reverse engineering things. So if we find capital Y, we've actually found this this exponential matrix as well. So we're going to be searching for one of these today. Okay, and we have Duhamel's principle for this, right? So if we're given an IVP, which of course you can think of now as a inhomogeneous non-autonomous Cauchy problem, and we found a fundamental matrix, so suppose we found this fundamental matrix, then all we have to do is compute the fundamental matrix on its inverse evaluated at the initial time, on the initial vector, and then we have our extra nice Duhamel's principle going on here, where I guess I missed an inverse here. There should be an inverse on that inside Y. So then this is going to look exactly like Duhamel's principle from the previous section, except we're replacing these matrix exponentials with fundamental matrices. And in some sense, just defining them as fundamental matrices means we can search for them in a manner which isn't the same as we were searching for the matrix exponential. And that's what kind of gives us a little bit of extra wiggle room here. So we're looking for them, but we're not necessarily forced to take a matrix exponential. Okay, this next theorem is interesting. So I'm mentioning that we can solve a boundary value problem now instead of an initial value problem with Duhamel's principle. And the reason why we can do that is if we start with maybe just like a boundary value problem here, so that's I haven't specified that all the t's are taking place at the same time. If I decide to write out the solution using my fundamental matrix on just some arbitrary vector c, so don't find c, the vector, yet. We just kind of compute our solution using Duhamel's, and I'm still missing my inverse there. We compute our solution using Duhamel's with some like arbitrary collection of coefficients c, and after we've computed that, we then turn around and say, hey, can I find out what each C should be with relation to these extra conditions on my ODE. Okay, so if they were all initial values, then you can just use your standard de Moivre's initial value solution. But if they're not initial values, maybe they're boundary values or something, then you actually just have to evaluate this, that, and that t at whatever time you're evaluating them, compute the solution, then you have a system. In other words, find C1, C2, dot, 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 CD with a system of D equations after using Duhamel's. So this is kind of how we can spread our wings away from initial value problems. You know, all these Cauchy problems we were tackling so far are all initial value problems. Can we spread our wings away from that and tackle some boundary value problems? And the answer is yes. We just kind of have to play around and say we're going to let our initial condition be like undefined right away, and then we're going to see if we can find maybe what the initial condition should have been based off of, you know, these boundary values that we've been given. And we'll see that in practice later in the book. So this is just a nice little theorem referencing that. Okay, so now let's talk about the most important theorem for linear ODEs. Okay, I'm calling it the most important theorem for linear ODEs, and that's the existence of a fundamental matrix. So I'm saying if I have y1, y2, yd minus 1, yd, a collection of d linearly independent solutions to my homogeneous ODE. So suppose for some strange reason I was able to solve for a collection of d linearly independent solutions to this ODE, then I can actually create a fundamental matrix just by placing each of my solutions. Right? I'm going to take all of my d solutions, they're linearly independent, I'm going to plug them into a matrix. This is just like when we were doing diagonalization. If I find d linearly independent eigenvalues, all I'm doing now is d linearly independent solutions. This is just like the matrix which diagonalized m, but now we're doing like a little different step. We're not really diagonalizing m, we're like finding the fundamental matrix for m in some sense. And all I do is I put them right next to each other, my d linearly independent solutions, and I get this big old matrix, but that matrix will in fact be a fundamental matrix. So that's a very important theorem, because what does it say? It says, this theorem says, in quotes, if I can find d linearly independent solutions to y prime equals mty, then I can solve the IVP, BVP, and inhomogeneous version. Because in some sense, that is the homogeneous version of the IVP or the ODE. And if I can find d linearly independent solutions to that homogeneous version, I can in fact solve any IVP, any BVP, or any inhomogeneous version, because I can construct a fundamental matrix. And so once I've constructed the fundamental matrix, then I just jump right up here to this problem, and there you go. This is my solution to the IVP or BVP under some choice of C's, which I can find just using linear algebra, and also the inhomogeneous version using Duhamel's principle. Okay, so let's look at this nice example. The example says, find the fundamental matrix of the following ODE. Right, so I'm not going to, notice that my m of t, so I'll say here, notice that m sub t cannot be written in the form m of t equals gamma of t m for some, constant in time m. That's what we liked in the previous section. If I try to factor out time, then I'm going to end up with a 1 over time in that term, and that's no longer going to be constant for me. So m of t is kind of sitting in this slightly more nasty territory of I don't know how to factor out gamma, which means I would perhaps have to calculate that calligraphic m, and I really do not want to calculate calligraphic m. So what I'm going to do instead is try to find solutions by other means. So let's see if we can do that. Well, I'm just gonna write this out directly. So y is y1, y2. I'm gonna take its derivatives, y1, y2 prime. I'm gonna take m, the matrix, and I'm gonna act it on y1, y2. And what I'm doing is I'm reversing this idea of having a system of linear ODEs into a vector valued ODE. I'm reversing that idea and I recovered the following system. But why is recovering a system actually easier than starting with the vector value ODEs? Well, in this case, it's particularly easier just because that does not depend on y2. Does not depend on y2. And since it doesn't depend on y2, let's pretend like it's its own equation. Pretend like it is a one-dimensional Cauchy problem. Namely, the Cauchy problem y prime equals ty. That's a one-dimensional Cauchy problem, and we know how to solve that Cauchy problem as y of t is some initial value, call the initial value y naught, e to the integral t dt, based off of one of those corollaries from earlier, right? The corollary said, you know, you can apply this with any dimension of vectors, but this is just a one-dimensional version of that. And so we get that y1 of t is precisely some initial condition, y10, e to the t squared over 2. If I scroll down, that's exactly what I've done here. My initial condition, e to the t squared over 2. So it turns out that rewriting my ODE, I end up with a one-dimensional ODE, and we know how to solve one-dimensional ODEs because they're a special case of our Cauchy problems. And so I get this solution. I don't know what y10 is, but I get a solution, e to the t squared over 2. If I plug that in, now that I know what y1t equals, I know this. So I know that right there. I'm just going to plug that in, and that gives me now a one-dimensional, this is 1D, let's see, it's non-autonomous, and it's inhomogeneous. But upon recognizing it's non-autonomous, inhomogeneous, I know how to solve it because, once again, that's one of my corollaries, which will let me solve this. So if I follow the corollary which lets me solve it, I compute using the matrix, right? The matrix exponential in one dimension is just like the exponential. So I take the exponential of the integral of gamma, take the exponential of the integral of gamma, compute across, go through, I mean, I can use a computer if I'm really feeling scared, compute across, and I get the following, right? And in particular, there's a slight typo here. That's supposed to be t squared over 2. But I recover the following for y2. Once again, I don't know what y20 or y10 are. They're just kind of like these arbitrary constants from my initial value problem, because I didn't really define an initial value problem. But now I've solved for y1 and y2, and so that tells me that y, which was y1 and y2, since I've just solved for them, there's y1, I'm plugging it in, there's y2, I'm plugging it in, and that's equal to y of t. If I want to, okay, this next step was me being sneaky. If I want to, I can rewrite this as a matrix acting on the initial condition y1, y2. And that's me being sneaky because that's me saying, okay, I've recognized this, that actually, in fact, this is the fundamental matrix, because that's how the fundamental matrix is defined. But suppose that maybe I wasn't so sneaky and I just wanted to find, how can I use this? Use this to find two linearly independent solutions to the original problem. Well, what I can do is I can choose special values for y1, 0 and y2, 0. And in fact, I'm just going to choose the very useful examples, 1 over 0 and 0 over 1, right, as my inputs here. And those give me the two linearly independent solutions. y1 is e to the t squared over 2, and t e to the t squared over 2. That's just me using this one. So if I plug this in for up here, I'm just taking the dot product across there, and I get the first column. There you go, y2 is 0, e to the t squared over 2. Okay, so there's two linearly independent solutions, and now that I have those, I can construct the fundamental matrix just by placing them right next to each other. Right, these fundamental matrices are constructed just like capital X for diagonalization. Maybe that's something to take away from today. Remember, capital Y of t is just like this capital X for diagonalization. They share an extreme number of useful parallels. So that's what we want to think every time. So since I have two linearly independent solutions, I can just put those in to the matrix to gain the fundamental matrix. Okay, so that's all I have for today. I know this is a little bit of a baptism by fire chapter. Just stick with me. We're going to make it through. Thank you very much. Bye.